Hi guys, welcome to today's video. This is 2018 paper 2, question 6. It's going to start off with a really common proof that comes up every few years that you need to know, as well as some common trigonometry, so let's get into it.
Okay, so here's our question. We're given a triangle ABC and we're told to prove that if the line L is parallel to BC and cuts AB in the ratio S is to T, where S and T are natural numbers, then it also cuts AC in the same ratio. Okay, so we've got a proof here, and we're first of all just going to write down what we're given in more concise terms. So I've just chosen to write it in two different bullet points. So we've got a triangle ABC, and then the rest of the problem then below that. So now we're just going to have to try and draw this up here in the space of the diagram. And there's a pretty easy way to do this. So first of all, we're just going to draw our triangle. So there we have it, and the points A, B, C. So next we're just going to draw the line XY, which we're told is parallel to BC. And because we've drawn BC as a nice horizontal line, it's going to be easy to draw XY as well. So there's XY, and we're just going to make that parallel to BC. And we're told that XY cuts AB, which is the left side of our triangle, in the ratio S is to T. So another way to interpret this is to say that the length of AX is S, and the length of XB is T. And that's all the information we have right now. So we're just going to move on to writing down what we've got to prove, which is that AY is to YC is actually the same as S to T as a ratio. Or in other words, when we look at the diagram, we're trying to show that if you compared AY to this line YC as a ratio, it would be the same as comparing AX over here to XB, because all a ratio really is, it's a comparison between two different values. And that's sort of a nice way to think about this. So the next thing to do now is try and do our construction. So the first part of our construction is to divide AB into S plus T equal parts, with S of them on AX and T of them on XB. So what this essentially means is that S and T is just any arbitrary ratio. So it's any numbers S and T that are natural. So in the case of this problem, we're going to let S be 3 and T be 2, but you can choose any number that you wish, because these are just arbitrary natural numbers. So that's going to look like this. And we're told that these parts are equal, so therefore all our little segments are equal along the side AB. And our second step of the construction is just to, through each new point, draw a line parallel to BC, which I've actually already done. That's just these little green lines that I drew after the first step, but that's it for the construction, which means that the only remaining thing to do is write down our proof. So first we're just going to say that by a previous theorem, which I'm just going to refer to as the transversal line theorem. The parallel lines cut off equal segments, or equal lengths, I should say, along the line AC. So we can now say that these lengths are equal all the way down to the bottom. And that's what the theorem that you also have to prove that can also come up, which is to say that if a transversal line is cut into equal segments by three parallel lines, then any other transversal line can also be cut into equal segments by those same lines. So that's not too important. You don't really have to reference that in this proof, but just to know which one it is. But again, you don't actually have to name this or anything in this proof. Next, we're going to say that we can then say that AC is divided into S and T equal parts, with S of them forming AY and T of them forming YC. So in other words, there are three equal parts up here, just as we had established when we did our construction, and there are two equal parts down here, which again we established during the construction. So we're starting to form similarities between the two sides of the triangle based on these parallel lines that we've drawn. And now we're going to say that K is the length of each segment on AC. So all of these small segments are all of length K, because they're all equal. Therefore we can write the ratio AY is to YC, which is the ratio of interest in this question, as KS is to KT, as it's clear that the whole length AY can be represented as 3K, and the whole length YC can be represented as 2K, so therefore that would be 3K is to 2K in our example. And because we can divide or multiply across a ratio by any number we choose, regardless of whether it's positive or negative, or whole, or fraction, or whatever, as long as we divide both sides of the ratio, we won't be changing the ratio itself. And because that's true, we can say that S is to T is also the ratio of AY is to YC. And that's actually the whole goal of this question, or this proof, which means that that's all we have to write. It's not actually a very long proof in the end. It's just a matter of remembering the important steps and making sure that you get your construction right and everything. And just so you know, if you get the original diagram right with no construction, you would get 4 marks. And if you also get the construction out perfectly correct, you're going to get 7 marks for that. Getting any 2 steps of the proof correct will get you 11 marks. And then actually getting out the whole proof, everything correct, will get you the 15 marks. Which means that's it for this question. Okay, so here's part B of the question. We're given the triangle ABC, which we did the proof on above, and we're given a bit of information about this particular example of that triangle and its lengths and its angles, so we're going to fill in some of that now. So they filled in the lengths for us. We're just going to, first of all, write down which lines are parallel. So we're told that XY is parallel to BC. So those 2 lines are parallel, and we're also told that XC and AC are parallel. So naturally this means that the quadrilateral XYZC is actually a parallelogram, which will come in handy. And we're also told that the ratio of AX to XB, so this line here, which is 4 centimeters, and this other line here, XB, is 1:2. So because we know that AX is 4, we can say that XB is twice that, which would mean that XB is 8. So that's very useful. And the only thing we have to do here is find the length of BZ. So we've got to find the length of this line at the bottom here. So first of all, we're going to try and use our lengths to determine something that we can use. So we have the length of the sides AX and AY, because we know it's 4 and 3. So we're going to use Pythagoras' theorem, given that we have a right angle, to find the length of the side XY. And many of you will already know the length of XY because this is quite a common triangle where you have 3, 4, and 5 as the sides. But we can still work it out with Pythagoras as well. So we can say that XY squared is 25 centimeters, which means that the length XY is going to be 5 centimeters. So we can fill that in. So the next thing to do now is recognize where we can actually implement the proof here. So how we can use that information. So we know that the line XY is parallel to BC and that it cuts the line AB in the ratio 1:2. But because of what we proved above in part A, we can actually say that it cuts AC in that same ratio, which means that the length of YC, or this length here, will be twice as big as 3. So therefore YC is 6 centimeters in length. So now the last thing we need to do before we can actually find BZ is see that in the parallelogram we have, we know the value of one side, YC over here, which means the opposite side to YC, which would be XZ, is the same length, which means that XZ is also 6 centimeters. And again, because we're dealing with parallel lines, we also know that all the angles in these triangles are the same. I won't go too much into the reasoning on that, but it's pretty obvious to see that these angles are equal, which means this angle is also 90 degrees. And that means that we're safe to use Pythagoras' theorem here because we have 2 sides and we can find BZ by using that. So then BZ, to B squared, is equal to the sum of 6 squared and 8 squared. It's actually just the triangle AXY scaled up by 2, but we're going to take the long route to finding the answer. So that's equal to 100, which means BZ is equal to the square root of 100, or it is equal to 10 centimeters. So now we found BZ, which is what we're asked to do. And there are actually lots of different ways to do this question because there's so many things you can just tell by looking at the diagram. And because you have parallel lines, it really opens up the possibilities of ways to approach this problem. But that's one way. And I would say it's a pretty nice question, not too bad at all. And for finding the value of BZ, you're going to get 10 marks. And that's actually it for this question. I hope you enjoyed the video. If you did, there's going to be other similar videos in the description, as well as some other helpful resources that you can use to help you out if you're feeling a bit stuck on trigonometry or proofs or whatever. So thanks for tuning in, and I'll see you next time.